We are live. Jackson, we said yesterday that friction depended on two things, mu, the coefficient of friction, and the normal force. And yesterday, because I was keeping it a little bit simple, I said, I don't know the normal force. Oh, but look, another force same size as the normal force. And everybody's, oh, it's mg. And that was yesterday. Now we're going to ask, what if there's extra vertical forces besides mg? We're going to use a little thought puzzle. Read along with me. It says this: consider the bench below, which is being pulled by student number one across a rough surface at a constant speed. You know what? Let's make student number one, just to give this some personality. Let's make student number one Annie. And you know what? The bench, let's make it those wood benches at the back of the gym. You all know the kind that are back there? You've seen them, yes? Okay, so Annie is sliding it. Now, we should underline this constant speed. That's very important. Suddenly, student number two, let's say Nate, pushes down, sits on the bench, because you've all seen someone pushing the bench and someone comes along and decides to sit on it while they're pushing. So Nathan comes and sits on the bench. If Annie maintains the same force as before, what happens to the A, weight of the bench, B, normal force of the bench, C, friction of the bench, and D, motion of the bench? But before we dive in, I suspect, you know what this might be a good job for? Thank you for picking up on my little awkward pause there. I did one here already. I had a little trouble with the lines. If we're going at a constant speed, F applied and friction should be exactly the same length. That's what constant speed would require, Newton's first. Okay? All right. Annie, what are the forces acting on this bench in the right-hand diagram? Get the obvious one. So draw mg the same length as the first arrow. Are we sinking into the ground like quicksand? Are we flying like Superman? So vertically, the forces must be balanced. There must be a normal force pointing up, bigger, smaller, or the same size as gravity. Not the same size. So here's what we want to think. See the extra push? That's Nathan. The normal force has to cancel out not just gravity, but the extra push. So the normal force is going to be larger than gravity in this case. And in fact, I can even tell you how much larger, however hard Nathan is pushing. If you're sitting on it, it would be your mg, whatever that would be. Okay. F applied hasn't changed. The question says you're still pulling with the same applied force. We introduced the concept of the applied force to you yesterday. If the normal force goes up, though, what other force goes up? Now be something like that, because friction equals mu times the normal force. Okay, so now let's answer the questions. A asks, what happens to the weight of the bench? When I say weight, what am I referring to? mg. Look at the arrow. Did mg change? Not mg. Right, Maya? Same. The weight of the bench did not change. So mg, same. Okay. What about the normal force in the second situation? Did that change? Yes. Normal force had to increase. My abbrev for increase or gets bigger is an arrow pointing up. Annie, you already pointed it out. What happened to friction then? Yep. And then it says, what's going to happen to the motion of the bench? Okay. First of all, what direction is the bench moving in the first picture? I think to the right. Yes? It's still moving to the right in the second picture, but is it speeding up or slowing down? So it's going to slow down and come to a stop. Okay? Newton's laws don't tell us which way you're moving. They tell us which way you're accelerating. But the fact that I know I'm moving right and friction is now winning, it's going to slow, and come to a stop. So, slow down, then stop. Is that okay? It says explain your answer using principles of physics. Cooper, I'm going to get more accurate and more complicated. I'm not going to ask this little next bit on a test, but if you've ever tried to slide something like really heavy where you can barely get it going, is it tougher to get it moving or is it tougher to keep it moving? Annie, you're right. You have to push harder to get it moving. Once you get it sliding, you can ease up a little bit. And the reason is, technically, if I'm being correct and nitpicky, there's two different kinds of coefficients of frictions. There's two mu's. There's a coefficient of friction when the object is at rest, and that coefficient of friction is a little larger. There's a coefficient of friction once the object is moving. Read along with me. It says this: there can be friction on an object even when it's at rest, since the hills and the valleys will lock up if we even apply a tiny force to the object. The force of friction on an object at rest is called static friction. I usually abbreviate that with a capital S because the word static means not moving or unchanging. Example 2. We're going to vote on this one. How high you hold your hand up is how sure you are of the answer. If we pull on a desk with a force of 2 newtons, I'm going to do it as an example. Sorry for those of you at YouTube. If I pull on this desk with a force of 2 newtons and the desk does not move, which it did not, which of the following statements is true? A, static friction is greater than 2 newtons. B, static friction is exactly 2 newtons. C, static friction is less than 2 newtons. Or D, no, there's no static friction. Let's vote. How high you hold your hand up is how sure you are of the answer. So if I pull on a desk and the desk does not move with 2 newtons of force, A, clearly static friction is greater than 2 newtons. I got 1, I got 2, I got 3, I got 4, I got 5, I got 6, I got 7, I got 8, I got 9, I got 10, I got 11, I got 12, I got 13, I got 14. Who says B, static friction is exactly 2 newtons? I got 1, I got 2. Less than 2 newtons. There is no static friction. Convince me. Yeah. Which one are you defending? Okay. What's your argument? Okay. But now we're starting out stopped. So if I pull this way with 2 newtons and you're telling me friction is bigger, which way must that desk accelerate? Did it? What's the correct answer, Maya? Has to be. Which one of Newton's laws did you use for that? Nope. Okay, so we have to write it out. Newton's first. You said 3. It's Newton's first. I don't know why you're going with what he says. He's got it wrong yesterday, too. So forces are, not listening, la, 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 can't hear you. Now, you could also have written down Newton's first and drop the mic, and I would totally get what you're getting at. Static friction is weird. Sorry again for those of you on YouTube. I'm going to keep picking on this table. Let's suppose the biggest that friction can be is 20 newtons. How many? How many? If I pull with 10 newtons, do you know how big friction is in that direction? Not 20. Exactly 10. Now I'm pulling harder with 12 newtons. Do you know how big friction is in the opposite direction? How do I know? Not accelerating, forces are balanced. I'm pulling with 19 newtons. I can tell it's almost ready to slide. It's 19 newtons. As soon as I go with 20.1, now friction can't match it. Also, as soon as it started to slide, I didn't have to pull as hard to keep it sliding. That's the weird phenomenon we're going to talk about, but I'm not going to test you on it. But a few years ago, a student asked me, Mr. Dueck, how come when I'm sliding furniture, it's really hard to get it moving, but once I get it sliding, I don't have to push as hard? So I added this. Yes? Well, no, because that would still work in outer space. If an object was at rest in outer space with no friction, it would still stay at rest in outer space. Newton was, he went full general. And again, one of the reasons we give him so much credit is in 1680, he was imagining outer space. I don't even think we built hot air balloons at that time, and he was already visualizing what it would be like out there. Full props to him. Static friction acts. Oh, good morning. Pause for a second here. Friction acts when you have two objects at rest relative to one another. If both objects are at rest, we say if you push on it and it doesn't move, static friction is the force that's resisting you. It's as big as it needs to be to cancel out your little push until you go bigger than it can be. Then you'll win and start to accelerate. So a block of wood, a static friction is what keeps a car with its parking brakes from sliding down a hill. A block of wood will remain stationary on a sloped table until you tilt it beyond a certain point, but it'll stay stationary because of static friction. The force required to overcome static friction, if you want to, you can underline this, is always greater than the force needed to balance sliding friction. Sliding friction is called kinetic friction, and I'm probably going to use a K as my abbrev for kinetic. And then, Evelyn, I have a word that starts with the letter P here, this next sentence. What word? I put presumably. There's still debate on why it's harder to get something moving than it is to keep something moving. I haven't dove into the research in about 5 years, but when last I looked, there was a few different theories that maybe complemented each other, but we didn't have a, hey, we've done the experiment to prove this is why. We know it's the case. If you ever start, by the way, as soon as you're out of high school, when you're in college, you start to move a lot of furniture because you and your friends are all moving out of your parents' houses. And the deal is, I'll help you move for pizza, and I know in a year you'll help me move for pizza. So you'll have about a 5-year window where you get pretty good at moving furniture, and you learn pretty quickly. Get it sliding, keep it sliding, don't let it stop if you can help it. Much easier to keep it going. So we think to overcome static friction, you have to break the welds before the objects can move relative to each other. You know what? Here is one analogy that I read, and this might be right, but we're not sure. How many of you have ever been in a vehicle driving on a gravel road that's really full of potholes when you're going really slow? And so you go into every single pothole, all the way down to the bottom, all the way up, all the way down. But then you may notice if you speed up a little bit, you can find a sweet spot where the vehicle will go over the pothole, start to fall, but by the time, before it gets all the way to the bottom, it'll catch the front of the edge of the front of the pothole, and you'll kind of be, but it's not as bumpy. We think maybe that's what's happening with those microscopic hills and valleys, maybe, but it's really tough to come up with an experiment at that small that we can see to prove it. Okay. Really then, if I wanted to be completely accurate, we should say something like, suppose we have a 5 kilogram object sitting on a surface, and static mu is 0.3. Kinetic mu, once you get it moving, is 0.25. A says, determine the force required to move the object. This is a job for a free body diagram. There it is. Jordan, what are the forces acting on this? Get the obvious one. Yep. Is it sinking into the ground like quicksand? Is it flying into the air like Superman? So there's a normal force, this case the same size as mg, not like the bench question we did a few minutes ago where the normal force was bigger. This wants us to find the applied force, the force required to move the object. And it's going to be when the applied force is 0.000001 newtons bigger than friction. So even though it says find the applied force, I'm going to find static friction, and I'll say if you go any bigger than that, it'll accelerate. So even though it wants me to find F applied, Nate, I'm going to find friction. Cody, friction is what times what? And since we haven't started moving yet, it's going to be mu s, the static coefficient of friction. I don't know the normal force. Oh, but look, 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 look. I know the force the same size as the normal force. Which one? Good. So it's going to be mu s mg. It's going to be 0.3 times 5 times 9.8. Which is what? Do that one in your head, Mr. Dueck. Well, maybe 5 times 9.8 is 49. It'd be 0.3 times 49. 0.3 times 50 would be 1.5. 14.7? No, yes? Yeah. So, how hard do I need to pull, Jordan, to get this to start to accelerate? Point. We really 14.700000001. Okay. So here we go. B. Lean, how hard are we pulling in part B? The object is pulled with what? Part B, what does it say? The object is being pulled with 10 newtons. How hard do we need to pull to get it to move in the first place? 14, basically more than 14.7. So what's the acceleration here going to be exactly as a number? Yes. And the force of friction will not be 14.7 because if you pull with 10 and friction is 14.7, can you have an acceleration of 0? No. How big is friction exactly in this case? 10 newtons. What if I pull with 12 newtons? What will the acceleration be? 0. What would friction be? 12 newtons. Okay? Static friction will match you as long as it can. It'll be as big as it needs to be to keep it at rest as long as it can until, ooh, Anderson, how hard are we pulling in part C? Now we're going to accelerate. Who's winning? F applied. Who's losing? Good. What's that always equal? What? Okay. Now, it looks like the first thing that part C wants me to find is the force of friction. So I'm going to draw a little line over here and I'm going to say friction equals mu times the normal force. Isn't the force of friction 14.7? No, we've started moving, so the mu is going to be the kinetic coefficient of friction, the slightly smaller one. We can still say, I don't know the normal force. Oh, but look, I know the force the same size as the normal force. So it's going to be 0.25 times 5 times 9.8. Do that one. Oh, yeah, I can do that in my head. It's going to be 49 divided by 4, 48 divided by 4, 12.25, I think. No longer 14.7. Nathan, trust me, if you start moving heavy objects, once you get them moving, you can use that. Oh, what else did part C want me to find, Anderson? The force of friction and Cooper's theorem. Divide by m. Okay. Anderson, what was the applied force in part C? 20 minus 12.25 divided by m. 5. Oh, I can do that in my head. 20 take away 12 is 8. It's going to be 7.75. What's a good way to divide by 5? Divide by 10 and times by 2. So it's going to be 0.775 times 2. It's going to be 1.5. Oh boy. 1.65? No, I'm off. Sorry? I carried a 1 wrong. Ah, got to show off that I botched it. 1.55 meters per second squared. Okay. Stop before you turn the page. This part will not be on Yes. I purely added that because Holly, a few years ago, a kid asked, Mr. Dueck, why is it that when I'm sliding something heavy, getting it moving is tough, keeping it moving not as tough? Because of that. So, to keep the math nice, we're going to treat both types of friction as the same thing. So friction is going to be mu times the normal force. I'm not going to distinguish between mu s or mu k. If I give you a coefficient of friction, use it for any situation. We're good. So where mu is the coefficient of friction, no units. And how will we find the normal force? Did I give you the normal force on a free body? Sorry, did I give you a normal force? I gave away the punchline. As an equation on your formula sheet? No. How will I find the normal force? This is a job for a from. Can I abbreviate free body diagram as FBD? If you don't know what that means, you can write out free body diagram, but let's abbreviate. I'm going to pause here, I think. Let me hit pause on the video.